interesting. All right. So you're given two binary trees, root 1 and root 2. Imagine that when you put one of them to cover the other, some nodes of the two trees are overlapped while the others are not. You need to merge the two trees into a new binary tree. The merge rule is that if two nodes overlap, then some node values up as the new value of the merged node. Otherwise, the not null node will be used as a node of the new tree. Return the merged tree. The merging process must start from the root nodes of both trees. So let's look at this example one. You've got these two trees. Let me make this bigger so you can see this. So here on the left hand side, you've got one binary tree, and this is a second one. They superimpose them and they add the values of each node to form the node of the resulting tree. So it looks straightforward. So if there is no node, then it's just a value of 0. So what they want you to do is you're given 200. There's a 2. We need to merge the two trees. Okay, return the merged tree. So I guess we just return the root node of the merged tree. Now a tree is represented here in Python, that's the language I'll use, as a node. Each node has a value, left pointer and a right pointer. You're passed root 1, root 2, and you're asked to return root of the merged tree. So, got 1, 3, 2, 5. Now, how will we do that? If we traversed both trees simultaneously and summed up the values at each node and stored the result in a new tree, we would obtain the resulting tree. Let's take a look at this example. We've got this represents this tree, this one represents that tree, and we want to add them up. Okay, so got the two root nodes. You start there. Let's say you do a DFS, a depth first search. Then you visit the root node, you add, then you, well, depth first search would, so you can do a pre-order, post-order, or in-order traversal. So depending on when you do the operation of adding. So just to refresh our memories, pre-order, let's look at that. So you say traverse concurrently, and if both nodes, left, right, contain values, then merge. Else the node which has value becomes the new node of the tree. Yes, that's the idea. So parasite, you've got the idea. Now it comes down to actually implementing it. So just a reminder for DFS, you can do pre-order, post-order, or in-order, right? Traversal of a tree. And a pre-order traversal entails visiting the node, then recursing on left and right. Whereas post-order would be recurse on left and right, then visit the node. And by visit, I mean perform the operation that you want. In our case, it would be the addition. And in order would be recurse on left, visit node, recurse on right. So if that's not clear, let me know. But that's just a general concept to understand. Now, let's say we do a pre-order, then basically we look at the values of the two nodes we have, we sum them up, we store them. Now, where do we store them? If you store them in a new node, then you would have to keep track of that new node, because that will be your tree. Then as you progress in traversing the two trees, you will need to keep track of that resulting tree that you're building as you go. So then this means we need a new function, or a new method in this case, which would take a third argument being the resulting tree that you're building. This isn't as simple as I thought, unless I'm missing something. I want to avoid looking at a solution yet. And yes, pre-order should be the easiest. But the logistics is what I'm trying to figure out now, because as you're building that resulting tree, you need to keep track of it, right? Okay, so let's run through the logic. Let's say we've got a method that takes 3 nodes, 2 being the 2 equivalent nodes from the trees we are summing, and the third node being the resulting node that we're building. But at that point in time, you still don't have that node because you're building it, so you wouldn't really, you would have the parent node. Try to see if there's a simpler solution though in building this tree. Like if we reused one of the existing trees, left or right, and just stored the solution, a result, into one of the trees, that would work, except what if it did not have a node there? Then you would have to create one for it. Or you can just append it. You can just have it point. Oh, okay. You can just have it point to the node that's missing. So let's look at this as an example. So we've got these 2 nodes. We add them up. 3. We store 3 in the second tree. Let's say that's going to be a result. Then we move on to the left, right, pre-order. Then for the left-hand side, we also do the same on this side. The function will recurse. You add 3 to 1, make it 4, and then go down left. Now this one wouldn't have a left node. When you realize that one of them is missing a left node, if the one that's missing the left node is the one that you're using as your result, what you do is you just take that left node and you just assign it here. So that self.left, instead of being equal to none, you will change it to be equal to whatever this. So even if there was a bigger tree down here under 5, it would automatically be assigned to 1. Okay, let's see if that works. So then you'd be done at that point. Then you go to right, visit the right child. This one has a right child, this one doesn't. So if the left-hand side doesn't have, you can just skip. You can safely skip and move on back up. So that could be a good solution. And in this case, we don't use additional memory. We are reusing the same tree. Do you see anything wrong with this logic before we try coding it up? Now the space complexity would be big O of 1 because you're not adding any additional space. You're just reusing one tree. And in fact, just updating some pointers to point to existing values. Time complexity would be just the traversal of the tree, so big O of n. as you're traversing the entire tree, or big O of, yeah, n, because n being the maximum of the number of nodes of either one of the two. I think this makes sense. If you think I am missing something, assuming there's still somebody listening, there's one viewer, apparently. Okay, I'm going to start coding this up. So we said we'll pick pre-order, and we will store the result in the second tree. Well, whichever is not null. If the second happens to be null, we'll just take the first one. Or first one if second is. Any other things to keep in mind? Okay. So I like Python because you can describe your answer in code, and it's almost like writing English. So can we reuse that same method here? Here, make a little more room. Get another monitor. So root 1, root 2, and we are trying to merge them. Okay. I just zoned out for a moment there. There's still one viewer, apparently, unless it counts me as a viewer. Is that still you, Parasite? Or have you left? If there is still a viewer, make yourself known. Is there a way to see participants? Oh, it's me. Alright, this was a good... Oh, you're still there. So why isn't it showing you on... Oh, there you are. Okay. So I guess only when you decide to type or when you're actively looking at the screen, if you're happen to look at something else, I guess. That's okay. Alright. Well, it's good to know that I'm not talking in the void. Alright. So let's give this a try. So now we're just going to assume no edge cases. Just look at it as is, as if it were fully populated. In fact, we can just focus on this problem on the left, and then we'll handle the edge cases. So we said that we will simply now, when do we return? That's another question. In a recursion, you need to have a base case where you return. And in this case, it's just a matter of visiting all the nodes. So if you properly code your pre-order traversal, it will handle that case automatically. So if we have an internal method, and this one will be merge DFS, and we will have our I'll just call it left node, right node, and that is all we need. Then basically the idea is that you will take... Correct, yes. Correct, but there's a slight complication here in the sense that when we're visiting the node or doing our operation, this is where you'll hit the base case, and I described that earlier, and look at it in a moment. So essentially, the visit portion, which is the sum, the addition, right? What you're doing is you're saying left node dot val here, right node dot val is equal to just plus equal, right? So essentially, we're adding them into the right node, and we will look at the case where the left node is null. And then, so this is kind of like our visit step, and what we do then is merge DFS, left node dot left, and right node dot left. I called it right node, but that's not really accurate. It should be a right tree node. So this should be left or first tree node. First tree, and this is second tree node. And those two nodes are the equivalent nodes. No, we said the second one is going to hold our result just to be consistent. And this is going to be like this, right? And so we go down the left hand side, and then we do merge BFS, first node dot right, and second tree node dot right. Okay, so at this point, this is the visit step, and this is this is recursing on the left hand side and then recursing on the right hand side. Now, there's what we'll do here is the following and then what do we return? Let's assume this is all good. What we return is so you've done the addition of these two nodes. So the caller will basically say merge DFS and then do root 1 and then root 2. So the caller will invoke merge DFS, root 1 and root 2. Merge DFS will take these two, add them into the second tree, and then invoke on the left and then on the right. And the whole result will be stored in the second tree, so technically you just return root 2. At that point, root 2 will hold the tree, the resulting tree. Now, what if root 2 is none? So let's handle that right here. If not root 2, if not root 2, return root 1. That's it. If we don't have a second tree, we just return the first tree. And if the first tree happens to be none as well, then we're just going to be returning none. Otherwise, we'll have a second tree, then we'll use it as a result. Okay, now let's go back here. So this is attempting to add the two trees. It adds the results of the first one onto the second one. And then here we're going to add the logic we talked about. So first on left. Before you do that, we said if we are missing, so let's write that down. If we do not have a left subtree for the first tree, what do? We can skip the step. That's skip. If we do not have a left subtree for the second tree. So the second tree, recall, that holds our result. And what do? We just take the first tree's subtree and add it. Then just use the first tree's subtree. I know it's a little confusing, but we'll put that in code here. So if we don't have a left tree for the first tree, so if I don't have not this, okay, what do? So if we don't have a first tree, so then just do nothing, skip, right? Pass for now, or just sort of pass, and we can adjust that condition. So if, and then if not second dot left, if you don't have a node for the second tree, what do we say? We just use the first subtree. So what we're going to do is we're going to do second tree node dot left is just going to be equal to first tree node dot left. We'll just set it to that. So if this was null, then we'll just set it to be for the second tree, because that holds our result. We'll set it to be the first tree. It's kind of like we're copying the first tree's entire subtree on the left-hand side into the second tree and skipping all the additions that need to be done there. We don't need to. And finally, else, then we know that we have subtrees in both cases. Then we need to do the merge. So this will be a base case. That's what I was saying, that this would be a base case. And so would this one. These two are not recursions, and they stop right there. Whereas that's the only recursion. These two just, this is a pass and this is a copy. Now let's do the same here. Right. And we will need a similar logic. Now I'm just translating the algorithm into a conditional here, and this could be cleaned up after. So if first tree node, okay, so now we're adding the right trees, the right subtrees. Now if the first subtree is missing one, what do? We pass. There's nothing to be added. If the second one is missing, on the other hand, then we need to do second tree node dot right is equal to second tree node second tree node is equal to first tree node dot right. Otherwise, if they both have right subtrees, then you do the merge. And okay, so this adds the values. This says do the left, do the right, and that one will return the results. Do we still have people alive here? Participants. Okay, so chat participants is only me. All right, does anybody see any problems with this? So here, we know when we call this, we are guaranteed. Now, what if root 1 is none? But not root 2. So let's do that. If not root 1, return root 2. If not root 2, return root 1. Otherwise, we know both are good and they're capable of being added. So then we go ahead and do this merge. And we take the second tree. This will hold our result. Yes, I just added that here. Thanks for the reminder. And so second tree node. So at this point here, when the roots are going to be called, we know for sure that they're not null. And so we add the value of the first one onto the second one. We're good. We have that result number 3. And then we commence the recursion. In the first case, both will have left subtree, so it will immediately go into this node. And then it will drop down. So I'm looking at this example here. It will drop down into 3 and 1. So it'll come back into this recursion. 3 and 1 will be added. Becomes 4. And then 4, we will look at the left subtrees. This one has a subtree, this one doesn't. So the first one has, the second one doesn't, so we're falling into this case. What do? We just copy the first one's left subtree into the second one, and we're done. And then we're out of this. We go and start working on the right, and the right is the exact opposite. The first tree doesn't have a right, so we're just going to pass because it already holds the result of 4. We're good. And so we're done with that recursion here. We will pop back up onto 3. We finished with the left-hand side. Now we do the right-hand side. The right-hand side, similar logic. So it looks like this will work. Now let's look at this. The 1 and 2. That as well. I feel like it will work. Okay, let's give this a try. Beautiful. So the test case passed. Now let's see if we have done well on the actual. Excellent. So this algorithm worked, and we are not bad on memory, but our speed is slow. Now, and it's comparing us only to Python submissions, so we can do better than that. Anybody have any thoughts for improvements? Now, this logic is a little too verbose. Maybe we'll leave that to another session, but this can definitely be improved upon. We can look at the solutions that people have had, but I'm satisfied. This is our first trial and for a live session, and we have 2 participants now. That's a record.